Today I'm going to talk about shear stress in beams. That is the beginning part of chapter 7, where we want to develop equations for determining how to calculate shear stresses in different beams. And we started with the basic concepts on what is shear force and how is that developed in the beam and how to calculate that in different cases. The first lecture is just focusing on the basic parts. This is very important because all the equations that we are going to use and develop somehow relies on this concept. I asked you on the course module to solve 3 problems. And by solving these 3 problems, I wanted to focus on 2 main things. First, how to calculate Q, capital Q, the first moment of area. Second, how to calculate the thickness that is required for determining shear stress in beams. These 2 topics are always confusing for students. Before talking about these 3 problems, let's review the basic concepts on what is the balancing force, how shear flow is developed, and what are the differences between different cases. Consider a beam that is subjected to 2 moments on the right and on the left. And I assume that the bending moment on the left and on the right are not equal to each other. We have already learned how to calculate bending stresses in the beams. So I'm going to take out one part of this element, as you can see, and I want to determine the bending stresses that are acting on that part. So looking at that from side, we can see the bending stress is going to be non-uniform on this section. It is actually 0 at the centroid, and it is linearly increasing when we get away from the centroid. The bending stress on the right and on the left are not equal to each other because the bending moment is different. So MC over I, when M is different, the bending stress would be different as well. Now, on that part, on that block that we took it out, we can determine how much would be the resultant force of those stress blocks on the right and on the left. I'm going to call them as F sub R and F sub L. F sub R stands for the resultant of stress block that are acting on that 10 rectangle on the right of the element. And F sub L is the resultant force of stress block on the left side of the element. As we can see, these 2 forces are not equal to each other because these 2 forces are developed by 2 different stresses that are having different magnitudes. In order for this element to maintain its equilibrium, there should be a balancing force, which is shown here by delta F. This balancing force is the difference between the force acting on the right side and the force acting on the left side. So this balancing force is the difference between these 2 forces. The contact area between these 2 parts is shown in red, and that is the area where the balancing force is developed. This balancing force, as we can see, is parallel to this cross-section area. And we have already learned that if the force is parallel to the cross-section area, it would develop shear stress. So there will be shear stress because of unbalanced moments that are acting on a section. All right. Now we want to determine how much is the magnitude of that and how to calculate that. So on the video, we talked about how to develop the equations all the way to the end. I'm not going to prove that again here, but let me remind you about this. In order to calculate the resultant force on the blocks, we have to integrate. But integration every time is time consuming. So instead of using the integration, after doing some calculations, we get to a simplified equation for determining how much is the balancing force. And we have seen that the balancing force is equal to delta M multiplied by capital Q divided by I. I is the moment of inertia for the section. Capital Q is the first moment of area for the section, and delta M is the difference between the moments. In the same way, we determine how much is shear flow. Shear flow is going to be the balancing force in the unit length of the element. So this delta F, if it's applied on 1 inch, on 1 meter, or 1 millimeter of the length of the beam, this is simply called the shear flow. So shear flow is delta F divided by delta X, and in a similar way, that would be equal to delta M divided by delta X multiplied by Q over I. Okay. The question that we want to focus on is, in order to calculate the first moment of area, which we already know, that would be area multiplied by D, what is the area that we need to consider? Also, what thickness we need to consider for the problem? So this is what we want to focus on this examples that we are going to review today. Okay, the first example that we have is similar to the animation that we talked about. There are two bending moments acting on the beam on the left and on the right. The length of the beam is given. Also, the moment of inertia for the entire section is provided, as well as the other dimensions for the section. And we want to determine how much is the first moment of area, how much is the shear flow, and how much is the shear stress. Okay, so the first step would be determining how much is the first moment of area. The first moment of area, or capital Q, is area multiplied by D. Area is going to be the area of the block where those stresses were acting on. So let me get back here. Remember that that first moment of area was derived from the integral of the stress block that is shown here. So we can see that that stress block is acting on the area of that separated rectangle. So area is going to be calculated for the rectangle that is hatched here. Area is going to be A multiplied by B in this problem. And the next property that we need to determine is D value. What is D? D is similar to what we have already used in determining the moment of inertia for the section. So if you remember, D is going to be Y bar minus YI. So Y bar, which is shown in red here, is the distance of the centroid of the entire section to the reference axis, which this problem I assume is on top of the section. So D is going to be the distance of the centroid of that block to the centroid of the entire section, which is shown here in orange. Now, let me calculate them one by one. So area is going to be A multiplied by B, and I'm going to plug in the values. D is Y bar minus YI, and we know that YI is B over 2. And now let's calculate Y bar. So Y bar is sum of the A multiplied by Y divided by sum of the areas. The first area is going to be A multiplied by B, and the distance of the centroid of that part to the top of the section is B divided by 2. And because there are two rectangles on the left and on the right, I'm going to multiply that by 2. The middle rectangle has the area of A multiplied by C, and the distance of the centroid of the blue rectangle to top is going to be C divided by 2. Then we are going to divide it by the total area, and we can determine how much is Y bar. After determining Y bar, we are going to plug that back into the D equation and determine how much is the distance of the centroid of that tan rectangle to the centroid of the entire section. Now, we can plug that back into the Q equation and determine the first moment of area. Okay, so this is the answer for the first part. How much is the first moment of area for this problem? The second part is determining the shear flow. Shear flow is going to be VQ divided by I. This is the equation that was approved on the video. But in this problem, shear force, or V, is not given. How can we solve this? There was an alternative equation for this problem, and that was V is already equal to delta M divided by delta X. So instead of V, I'm going to use delta M divided by delta X multiplied by Q divided by I. Okay, now I'm going to plug in the values. Delta M is the difference between the moments. The moments are given in pound-feet, so make sure to multiply them by 12 to convert them into inch, divided by delta X, which is the length of the element, and then multiplied by the first moment of area and divided by the moment of inertia. This is giving us how much is the shear flow in the beam, which in this problem is 31.24 pounds per inch. What does it mean? It means that in one unit length of the beam, a force of 31.24 pounds should be transferred from that tan block to the rest of the section. Okay? Now I want to determine how much is shear stress. Shear stress is a shear flow divided by the thickness. Now we get to the second important question. What is the thickness that we need to consider for this problem? In order to calculate the thickness, remember how the shear stress is developed. Shear stress is force divided by area. So force is that balancing force that we just calculated. Remember, balancing force in the unit length is shear flow, or lowercase q, that we just calculated. So if I want to determine how much is shear force in this problem, how would I determine that? Shear stress is delta F, or balancing force, divided by this red cross-section area. Now, because I have determined shear flow, which is the balancing force in the unit length, it means that I'm going to consider the area for 1 unit length of the beam. So L, or delta X, is going to be 1 inch. But how much would be area in that case? The area of this rectangle for the unit length would be 1 multiplied by this dimension. So this is going to be the thickness that we are going to consider. So again, the area for this red rectangle for the unit length would be height of that section multiplied by 1. So in this case, as we can see, the thickness is the thickness of the contact area where that tan block is connected to the rest of the section. So the thickness that is going to be considered is going to be the thickness of the contact area between these two parts, which is given to be B. So T in this problem is equal to B, and I'm going to plug in the values and calculate how much is the shear stress in this case. Okay, the second problem is kind of similar to this, but the difference is that in that problem, there is just one block on top of the section, and it is connected to the rest of the section. So the moment is the same, the dimensions are the same, the moment of inertia is the same, and the only difference would be that we have a one block on top, which is connected to one block on the bottom. Okay, in order to solve this problem, again, we need to determine what is Q. So how can I calculate Q for this problem? How can I calculate the first moment of area? Remember, the first moment of area is calculated based on the fact that where the bending stress is acting on the section. So in this problem, the bending stress is going to be developed on the entire tan section on top. So in order to calculate Q, I need to consider the area for the entire tan section on top. All right, I'm going to write down the equations here. Q is going to be area multiplied by D. Area in this case is going to be 3A multiplied by B. D in a similar way is defined as the distance of the centroid of this tan rectangle to the centroid of the entire section. And in this case, because the height of section is similar to the previous problem, D is going to remain the same. The only thing that has changed for the calculation of Q would be area, which is now 3 times higher. Area is going to be 3 times higher than the previous case. D is going to be the same as the previous one. And I'm going to calculate Q, which is 3 times higher than the Q that we got before, because the area is multiplied by 3, D remains the same. Okay. Now we get to the second part. How can I calculate the shear flow for this problem? In order to calculate the shear flow, we're going to use the same equation as we had before. Q is VQ over I, or delta M divided by delta X multiplied by Q divided by I. So delta M is the same as the previous case, and Q is now 3 times higher, delta X is the same, I is the same. It means that shear flow is going to be 3 times higher than the previous case. Now, the shear force that has to be transferred is 93.7 pound over inch. And that makes sense because look at this block, the tan block on top. It is 3 times larger than the previous block that we separated before. That means that in this case, the shear flow is also going to be 3 times larger. Okay, now we get to the last part. What is shear stress? Shear stress is shear flow divided by the thickness. But what is the thickness that we need to consider for this problem? This is the section that we have. We need to see what area is that balancing force developed on. So I'm going to separate these two parts. This is going to be the area where the balancing force is acting on, which is shown in red. This is going to be the balancing force acting on that contact area between these two parts, and I need to consider the thickness of that contact area. All right, how much is this area for the unit length? That would be equal to 1, which is the length of the element, multiplied by the thickness of that blue shape, which is shown as T sub W. Okay, so again, the rule of thumb for determining the thickness. Thickness is always dimension of the contact area between the parts that we want to calculate shear stress between them. So in this case, I'm going to show that in red again here, and that is going to be the thickness. And the thickness in this case is given to be A. I'm going to plug in the values of shear flow and A and calculate how much is shear stress in this problem. Again, I want to highlight what are the differences and similarities between these two problems. The last problem is similar to the first problem. The only difference is that instead of having the moments, we were given the shear force acting on the right and on the left of the section. In order to calculate the first moment of area, is there any change between this problem and the first problem? No, that is going to be exactly the same. So I just go and repeat the process, and Q would be exactly the same as the first problem. Is there any change between this problem and the first problem on calculating the shear flow? Yes, there will be a difference. In this case, we were not given the moments, so I cannot calculate the difference between the moments. I actually don't need to do that because the shear force is directly given, and that means that I can use the original shear flow equation, which is VQ divided by I. So let me do that here. V is given to be 1,200 pounds, and multiply that by Q divided by I, and that gives us the shear flow. And the third step, is there any difference between this problem and the first problem? The contact area is again the contact thickness between the tan block on the left and the rest of the section, which is the same. And we can calculate how much is shear stress. Shear stress is not the same as the first problem, of course, because shear flow is different, but the thickness was the same between these two problems. All right, any question for this problem? Or all of these problems together? Again, we wanted to review these problems to make sure that we understand two important things that are sometimes confusing. How to calculate Q, or the first moment of area for the problems, and how to calculate the thickness that is needed for determining the shear stress in the problems.
So basically what you're saying in this problem is that the only difference is the contact area?
There are two differences between this problem and the previous problem. One of them, as you said, is the contact area. So,
or the thickness of the contact area.
Yes, the thickness of the contact area is now A.
Right.
But Q is also changed, the first moment of area. Q is now 3 times higher than the first case because we are determining the bending stress that are developed on the entire tan block. That is now 3 times larger than the previous case.
Okay.
On the last one, you had 2 blocks. Why didn't the other block count into calculation?
Okay, good question. What I did was I considered the area for the left block and calculated Q for that left block and considered this thickness, that is the contact area between that block and the rest of the section, and calculated the shear stress between these two parts. The reason that I did that was because I wanted to determine how much is the shear stress between that block on the left side and the rest of the section. But can I solve this problem by considering both tan blocks on the left and on the right? Let's do that and see what is happening in that case. In addition to the left block, if I consider the right block, what would be the Q value in this case? Area is doubled, D is going to be the same, right? So in that case, Q is going to be 2 times larger than the previous case. So if I calculate the first step, Q is going to be 63.6 for the first moment of area. It's 2 times larger than the Q that we calculated for the problem that I solved. Now let's go to the shear flow. How much would be the shear flow then? Delta M, delta X, and I are the same. Q is doubled, so shear flow is going to be twice larger than we just calculated. Now let's go to the shear stress. If we calculate shear stress, that would be shear flow divided by the thickness. What is the thickness in that case? Now we have 2 blocks that are connected to the middle part. There will be 2 contact areas here. So now the thickness is going to be 2 multiplied by B. And if I go back to this page and calculate the shear stress, the shear flow is doubled, but also the thickness is doubled as well. It means that the total shear stress is going to be the same. So we can consider both blocks on the left and on the right, but that is not going to change the magnitude of shear stress in this problem. Did I answer your question?
Yeah, thank you.
All right, yes. So the question is, can we have a situation where block 1 and block 2 are having different dimensions? And in that case, the Q is not doubled and the thickness is not the same on the left and on the right? Yes, we can have a non-symmetric sections where the dimensions are not the same. If we want to determine the shear stress in that case, then we need to split them into different parts and calculate shear stress on each part separately, because shear stress in that case are not going to be the same on each of those parts. The rule of thumb is, if we want to determine the Q and the thickness, we need to see what is the point where we want to determine shear stress. Once we identify that, then we are going to cut the section passing through that point, and then calculate Q for the cut section, and the thickness would be the contact area between the cut section and the rest of the section. This is what I want to highlight today. This is all about the concept that I want to discuss today.